Okay, in this video we're going to be looking at partial fractions as a strategy for integration, sometimes called partial fraction decomposition. And so before we run into actual partial fraction decomposition, we're going to look at a problem, how to integrate this integral of 1 over x squared minus 9. We're going to do it with a trig substitution, which we covered in the last set of videos. And then we're going to look at it using partial fraction decomposition. All right, so this is the form of an x squared minus a squared. And so we're going to let x equal 3 secant of theta as our substitution. Dx is equal to 3 secant theta tangent theta d theta. And then we'll draw a reference triangle just to help ourselves out. So the secant is going to be x over 3, which is the hypotenuse over the adjacent side. Using the Pythagorean theorem to find the opposite sign, that's going to be the square root of x squared minus 9. If we use the tangent of theta, that is going to be the square root of x squared minus 9 all over 3. And then we'll multiply both sides by 3, and we'll have 3 tangent of theta is equal to the square root of x squared minus 9. If we square both sides, then we'll have 9 tangent squared theta is equal to the denominator of x squared minus 9. So what we'll go and do from here is to replace differential dx with 3 secant theta, tangent theta, d theta. And we'll replace the x squared minus 9 with a 9 tangent squared of theta. Factor out a 1/3 and we'll simplify. And so we'll have the secant of theta divided by the tangent of theta. So this will be 1/3. Rewrite secant as 1 over cosine. Rewrite tangent as sine over cosine d theta. And that's going to be 1/3 integral of 1 over cosine of theta times the reciprocal of the tangent, which is going to be cosine over sine. And that'll simplify down to 1/3 integral of 1 over sine d theta, which is 1/3 integral of the cosecant of theta. And the integral of cosecant is going to be negative natural log absolute value of the cosecant of x plus the cotangent of x. And pardon me here, we're using variable x. So let's go ahead and put, we're using variable theta. So let's put those thetas in there. Sorry, they weren't x's. Okay, and then plus your constant of integration. So 1/3, we'll slide the negative out. ln absolute value, cosecant is going to be the hypotenuse over the opposite side, so x over the square root of x squared minus 9, and the cotangent is going to be the adjacent over the opposite, so the 3 over the x squared minus 9, and then plus c. Okay, so we're going to take a look at this again, and we're going to use partial fraction decomposition, and then we'll show that this antiderivative is equivalent to the antiderivative we get using the partial fraction decomposition. All right, so the idea here is 1 over x squared minus 9. X squared minus 9 is the difference of squares. It factors into x minus 3 and x plus 3. So is there a way I could factor that? Is there a way I can write that as two fractions, a over x minus 3 plus b over x plus 3? And so that's the whole thing, a partial fraction decomposition. So 1 over x squared minus 9 is a little bit more difficult to integrate, but a over x minus 3 and b over x plus 3, those are both natural logs. So the integral of a over x minus 3 would be a ln absolute value of x minus 3, and integral of b over x plus 3 would be b ln absolute value of x plus 3. So they're much simpler integrals. We're going to go ahead and clear the fraction. The LCD here is x minus 3 and x plus 3. So we'll go ahead and multiply both sides by x minus 3 and x plus 3. That'll clear the fraction, so we'll have 1 is equal to a times x plus 3 plus b times x minus 3. And I've seen a variety of different ways of doing this. Some folks like to pick values for x and then solve for a and b. So for example, we'd let x equal negative 3, and then x equals positive 3, and that would allow us to solve for the a and the b. This strategy will also work where we go ahead and distribute, so we have ax plus 3a plus bx minus 3b. And the idea is we have two equal polynomials. The polynomial on the left-hand side is just 1, and the polynomial on the right-hand side is the ax plus 3a plus bx minus 3b. So we want the coefficients of the x's to agree and also the constants. Well, there are no x's on the left-hand side of the equation, so we'll have 0 is equal to a plus b. Then for the constants, the constant 1 is going to be equal to the constants 3a minus 3b. And so now this is a system of equations, a system of two equations and two unknowns, so we can solve this by the elimination method or substitution. I'm going to elect to solve by the elimination method, and I'm going to multiply the top equation by 3, so it gives me 0 equals 3a plus 3b, and the bottom equation 1 equals 3a minus 3b. And then what happens when I add those, 0 plus 1 is 0, 3a plus 3a is 6a, and then the 3b minus 3b, those cancel out. And so this gives me 1 is equal to 6a. Divide both sides by 6. And so we have 1 6 is equal to a. Now, we can use either one of the equations that we have there. 0 equals a plus b, 1 equals 3a minus 3b. And I'm going to use the 0 is equal to a plus b, and a is 1 6. So 0 is equal to 1 6 plus b. And so that would tell us that b is equal to negative 1 6. So if this works out, 1 over x squared minus 9 should be equal to 1 6, 1 over x minus 3 minus 1 over x plus 3. And so we're going to see if that's in fact equality or not. Now if we wanted to put the 1 6 in, you'd put it here, and so we'd have the a right here and the b right there. I just went ahead and factored the 1 6 out. Okay, so again, question mark over the equal sign. Are they in fact equal? So what I'm going to do is I'm going to get common denominators. So the first fraction you need to multiply by x plus 3 over x plus 3. And the second equation you need to multiply by x minus 3 and x minus 3. And by the way, I did take these off. That was just to show. So this should just be 1's up there now. Okay. So again, 1 times the x plus 3 is x plus 3, and then negative 1 times the x minus 3 is x minus 3. And so doing that, it gives us the common denominator of x plus 3 times x minus 3, or x squared minus 9. Okay, so then that's going to give us 1 6, 6 over x squared minus 9. The 1 6 and the 6 will absorb, and so we do, in fact, have equality there. So this partial fraction decomposition seemed to work okay. All right, now let's go ahead and actually integrate this. So the integral of dx over x squared minus 9 using partial fraction decomposition was 1 6 times 1 over x minus 3 minus 1 over x plus 3 dx. So it's going to give us 1 6 natural log of the absolute value of x minus 3 minus the natural log of the absolute value of x plus 3, and then plus c. Okay. So is that the same as when we used the trig substitution? And when we did the trig substitution, we had negative 1/3 ln absolute value of x over x squared minus 9 plus 3 over the square root of x squared plus 9, and then x squared minus 9, and then plus the constant of integration there. And so what we're going to do is we'll go ahead and combine the numerators, because they have a common denominator, and so it's going to be x plus 3. X squared minus 9, we'll factor that into x minus 3 and x plus 3. And then the square root, we can go ahead and put on each factor there. Square root is 1/2 power. Okay. Then we're going to reduce. And so that's going to be x plus 3 to the 1/2 power divided by x minus 3 to the 1/2 power plus constant integration. Okay. And then we'll rewrite that as x plus 3 over x minus 3 in the natural log to the 1/2 power. Okay. Oh, and don't forget our plus c here. Plus c. Okay. Then we're going to use property of logarithms, power rule, to bring down the 1/2 as a factor. So that becomes negative 1/3 times 1/2. ln absolute value of x plus 3 over x minus 3. Don't forget our constant of integration. Okay. So it gives us negative 1 6. ln absolute value of x plus 3 minus ln absolute value of x minus 3. And I use the quotient rule for logarithms to split up that x plus 3 divided by x minus 3. Okay. And so that gives us 1 6. I'm going to go ahead and put the negative back in, so 1/6 ln absolute value of x minus 3 minus ln absolute value of x plus 3. And so that you can see that the two integrals are in fact the same, although they don't look like it at the beginning. We had to do some algebra to make one look like the other. Okay, so stay tuned for the next video, and we'll do some more examples of partial fraction decomposition. So we'll see you next time.